So this is chapter 10, part 1. My book goes in a different order than yours, but I know you've done this, and it'll probably be on the final, so I thought I would talk a little bit about it. I said, why does anyone remember Dr. Check giving an explanation as to why moles had to be invented? The concept of moles had to be invented because it allows things to be counted by weighing. Atoms are so small that it's not practical to weigh them. So what can you do if you can't weigh something? How can you count then? Well, when it comes to gases, what we find out is that the volume of a gas is proportional to how many moles. A larger balloon has more moles than a small balloon, fewer moles. Now I realize this is a picture, but just imagine that these balloons were all in the same plane. The bigger balloon has more moles of gas than the little. So here on the left, we have these balloons are filled with nearly equal amounts of gas at the same temperature and pressure. One yellow balloon contains helium, a low-density gas. The other balloon contains air. So if you measured the size of these, they basically are saying that these would be the same, but the only difference is that these molecules weigh more. But they're the same number. Now, when you look at these hot air balloons, how do they make hot air balloons rise? They heat them up. And so therefore the balloon gets bigger, but you have the same amount of gas in it. And so then it rises. You actually lower the density by heating, which expands. Remember that density is equal to mass over volume. In the case of the hot air balloon, the mass is constant, but the volume is increased. And so that means that the density is going to go down. So gases are different than condensed states. A bunch of texts are coming over here. I don't know if that shows up on the video, but we'll see. Gas volumes are different because their volumes change significantly with pressure. Solids and liquids are not greatly affected by pressure. Gas volumes change significantly with temperature, but that doesn't happen to liquids or solids. Gases expand when heated and shrink when cooled. The volume change is 50 to 100 times greater for gases than liquids and solids. Gases flow freely, gases have relatively low densities, and gases form a solution in any proportion. They are freely miscible with each other. So here are the three states of matter. The big deal about gases is that there is a lot of empty space. In liquids, particles are in contact, but they get to move around one another. In solids, everything is in a fixed lattice. If you remember, pressure is equal to force over area. Atmospheric pressure, so here's the Earth, and all of the air that's above us is being pulled down by gravity, and so all of that pressure exerts a force on the surface. Atmospheric pressure decreases with altitude. So if you're on top of a mountain, you have less pressure than at the bottom of the mountain. You have more pressure because there's less air if you're up in the mountains. The effect of atmospheric pressure on a familiar object is demonstrated by taking out all the air out of this can, and then the atmospheric pressure crushes the can because there's no air in it. The vacuum, if you turn the vacuum on, the pressure outside is greater than the pressure inside. This is how a barometer works. On a high pressure day, there's more atmosphere. So if you think of the atmosphere as a sea of air, so here we are on Earth, high pressure, if you look on a weather map, means that the air is thicker above that spot. And low pressure has less air above that spot. So if you think of this blue arrow as representing the arrows in my picture, it will hold up more or less mercury depending on what kind of day it is. Usually it's better weather with high pressure, and storms are usually associated with low pressure. This is called a closed-end manometer. You could determine what the pressure is of the gas, this orange gas, just by measuring the difference in these heights of the mercury, because this is a vacuum. So this doesn't have any effect on the pressure on the gas. Here, the only pressure on the gas is this difference in height. So let's say, for example, this was 20 millimeters of mercury, then the pressure of the gas is equal to 20 millimeters of mercury. Okay. In an open-end manometer, then you have to contend with the fact that you have whatever the atmosphere is that day. So let's say this is 760 on that particular day. The pressure of the atmosphere is 760. And this difference in height here is 20 millimeters of mercury. And this is 20 millimeters of mercury. The pressure of the gas here is going to be equal to the 760 minus 20, which is equal to 740. So the orange gas has a pressure of 740 millimeters of mercury. Over here, you could see that this pressure of the gas is stronger. It's holding up not only 20 millimeters of mercury, but it's also pressing against the 760. So this one is 780 millimeters of mercury. Okay, these should be deltas. Okay, so this one's 740, this one's 780. This is open end. Here's some common units that you may need to do conversions. 1 ATM is equivalent to the 760 millimeters of mercury that we talked about earlier. Sometimes you'll see pascals or kilopascals used. When you go to fill up air in the tires at the gas station, they use pounds per square inch. So 1 atmosphere is 14.7 pounds per square inch. Torr is basically the same as millimeters of mercury. And then sometimes weathermen use bar. So a geochemist heats a limestone sample and collects the CO2 released in a flask attached to a closed-end manometer. After the system comes to room temperature, the difference in the height is 291.4 millimeters of mercury. Calculate in torrs, atmospheres, and kilopascals. If you use the correct conversion factors, you can get these answers. The gas laws describe the physical behavior of gases in terms of 4 variables: pressure, temperature, volume, and amount. An ideal gas is a gas that exhibits linear relationships among these variables. No ideal gas actually exists, but most simple gases behave nearly ideally at ordinary temperatures and pressures. There's no way for you to know this, but Mommy and I just went to dinner at an Indian restaurant, and it's 2 hours later. All right, where do we have here? We're at gas laws, okay. All right, what have I got here? Boyle's law, the relationship between volume and pressure of a gas. So this basically shows the inverse relationship of volume and pressure. Notice that the plot of volume versus 1 over pressure is linear. This also shows that the product is a constant. The product of P and V is a constant. I know these are things you already know, but this lays it out very formally. It also kind of shows you the experiment that Boyle did. He had one of these J tubes. There was some gas trapped inside the left-hand side, the orangish gas, and notice that as he increased the mercury that he poured in, the just to let you know what these numbers are, this difference in height is the difference between the right side of the tube and the left side of the tube. The atmospheric pressure is constant because that's basically the several miles of air above, and then adding the difference in height due to the mercury is adding in this column here. So when you add the two together, you get the total. And that's how they got the pressure total that they plotted. 1 over that is this. The product of P times V is this. And you see that it's a constant. So that's Boyle's law. So I would say that proportional. At constant temperature, the volume occupied by a fixed amount of gas is inversely proportional to the external pressure. And these are things that are sensible. Charles' law is the one that demonstrates the relationship between volume and temperature. And so what they have here is they have gas trapped inside this glass tube, and there's kind of a cap on it. Basically, it's just a plug. It's a bit of liquid mercury that can rise or fall depending on the volume of the gas. And so what happens is if you heat the water, that's going to heat the gas, and the gas is going to expand. The pressure is basically constant because it's just atmospheric pressure plus a tiny bit of whatever the mercury is, but you don't have to care about that. The point is, though, is when they raised the temperature here about 100 degrees Kelvin, there was a substantial increase in the volume of the gas. And if you do a plot, you could see volume versus temperature is directly proportional. The thing that was kind of interesting is that the reason you get these different colors basically have to do with a difference in moles. So that's just going to affect the slope. But the relationship is basically the same. The volume is proportional to the temperature. It's not equal to the temperature, it's proportional. Guy named Kelvin is the person that first noticed that all of these straight lines end up hitting at exactly the same point, which was minus 273 Celsius. He called that absolute zero because what he proposed was that molecules could never be colder than that, because this was the point where the molecules froze into a solid, and it was a perfect solid that couldn't get any smaller. So it couldn't get any colder. So volume is proportional to temperature, V over T is a constant, and that's what we want in the previous slide. This is the relationship between the volume and amount of a gas. So here they take 0.10 moles. Notice what they did is they actually had some solid dry ice, and they let the dry ice convert into the gas phase, and that's what's colored here. But if they double the amount of CO2, notice that the volume that comes out is twice as big. The pressure is exactly the same. It's atmospheric pressure, whatever the pressure is that day. So here we're going to see that volume is proportional to moles. So if one goes up, you increase the moles, you increase the volume. That's really proportional. STP, or standard temperature and pressure, I know you know that because you used it in a problem earlier in the semester. That specifies 1 atm and a temperature of 0 Celsius. Now at those measurements, only those measurements, the volume of the gas is 22.4. I remember one time you just kind of threw this number in. This is only true at STP. Okay? If you change the temperature at all or the pressure, you don't have 22.4 liters of gas. This actually brings us back to what we had earlier of the pictures of the balloons. When you have a balloon of one gas and you compare it to another balloon of a different gas, if the balloons are exactly the same size, this is what's kind of amazing. They have exactly the same number of particles inside, or the same number of moles. Okay, that's basically saying the same thing. There's 1 mole of gas in each of these balloons, as long as, look, Margaret, pressure and temperature are 1 atm and 0 Celsius. This is at STP. Now, if you change the temperature for all of the gases, they still would all contain 1 mole of gas, but they wouldn't be 22.4 liters. It would be a different liter. So if you cooled off, the volume would go down. Or if you heat up, the volume would go up. Okay? But, because that just means it wouldn't be 22.4. The volume of 1 mole of an ideal gas in some familiar objects. So they're saying here 2 liters of a carbonated drink, a gallon of milk, 22.4 liters is 1 mole of gas. It occupies a pretty big volume. Whereas let's say you had 12 grams of carbon, that could easily fit in your hand. That's because the carbon atoms are bound to each other. The ideal gas law, calculated at STP, allows you to calculate the value of R. You just plug in the 22.4 liters, 0 Celsius is what that is, and 1 ATM and 1 mole, you get the R value, the universal liquid gas constant. So you could do problems like where if you change some of the conditions, you could figure out what the new variable is. The laws that we mentioned earlier basically get all combined in the ideal gas law. So you'll see Boyle's law, Charles' law, and Avogadro's law all contain a constant in it. That's not R. That's a constant just for those 2 variables. The R value is when you have all 4 variables. So here's an example problem you can try. Boyle's apprentice finds that the air trapped in a J tube occupies 24.8 cubic centimeters at 1.12 atm. By adding mercury, he increases the pressure to 2.64. Assuming constant temperature, what's the new volume of air? The constant temperature is key because that means you don't have to use all of the full ideal gas law. You could just use Boyle's law, pressure and volume. I would use this, and I would solve for V2. And this is the work. I'm sure you could do it on your own and compare it to the answer here. Tell me if it's should be right. A steel tank used for fuel delivery is fitted with a safety valve that opens when the internal pressure exceeds 1 × 10⁻³ torr. It is filled with methane at this temperature and this pressure and placed in boiling water at exactly this temperature. Will the safety valve open? Basically, will the new pressure be greater than 1.0 × 10⁻³ torr? Okay, so this is one where you have T and P. So you do P1 over T1 equals P2 over T2. You want to solve for the new P2. Make sure units are all correct. So you have to have Kelvin for temperature. And probably the best thing to do is take that original atmospheres and convert to torr. Okay, and then you solve for this one. And on the next slide, turns out the safety valve will not open. Here's another one. I'll let you do that on your own. And lots of practice. I think I'm going to mention this one and then let you work on these problems for review. And then you could contact me if you have any trouble or questions. Basically, all that this problem is a variation on the ideal gas law in which you make a substitution. Because the moles of any sample is its mass divided by its molar mass. And that will allow you to rearrange this so that you get density. Because density is mass times volume. And just, I've got a couple problems on here that you could try and compare the answers. All right, I'm pretty tired. I think I'll try to do another one tomorrow. And I really hope this helped. Bye.